And now I'm going to introduce Myeongsoo Shin. So he's a designer at NAVER LABS Korea. He's an interaction designer in NAVER LABS Korea, specializing in human-robot interactions. His work ranges from designing delivery robots at 7084 in Korea to designing robots for data center automation, bridging user needs and technology. So his presentation, HRI in the second DC project, will share the design challenges and trials in implementing robotic system at NAVER's new data center called Gak Sejong. So yeah, please welcome him.
Morning, everyone. My name is Myeongsoo Shin. I'm an interaction designer from NAVER LABS Korea. I came here to share our experience on designing the HRI in the for the robotic systems, implementing the system to NAVER's new data center. First up for my presentation, I will introduce what our robotic systems look like. And second up, I will cover the challenges and some difficulties we faced in the design process, and how do we try to implement the design in real field. Before diving into the main presentation, I wanted to introduce NAVER and NAVER Labs, but since Martin already covered that yesterday, so I will skip it. Yeah? Instead, I want to introduce my team in NAVER Labs. Me and my colleagues are part of design team at NAVER Labs. And we work on various projects. And our human-robot interaction team, which is my team, focuses on the physical and functional aspect of robots and developing and applying the service scenarios and behaviors and interaction modalities. The platform design team designs the robot management systems like the robot central robot controlling system, and some service operation tools, and aiming for the scalable and adaptable platform that balances service requirements. And the last team of the design group is the product design team. And the team handles the physical design of the robot embodiment, GUI, and the visual elements that shape how robot functions. NAVER Labs has developed two large-scale robot services. The first is the 1784 project, which operates almost 100 robots in NAVER's new headquarters. And the second is the second DC project, and which supports asset and human movement in the large scale, our new data center. 2 years ago, our team member Sure introduced the 1784 project at this symposium. So today I will focus on 2NDC. Yesterday, as Martin introduced, 1784 is the name of NAVER's second headquarters. And it is the world's first robot-friendly building, and it has specifically have robot-only elevators and centrally controlled doors and elevators, and flat floors without the thresholds for the robot movement, and the building finishes that support the function for visual localization and LiDAR of the robot, and desk layouts for a smooth robot path. And the second DIS project is an initiative to revolutionize NAVER's second data center called Gak Sejong. Based on the advanced technology developed for 1784, and the architecture and infrastructure expertise from 1784 has been fully integrated into 2NDC. Along with new technologies to manage large-scale servers and the extensive site. By the way, it's the building of the data center. The end of the data center and the other end, the distance between it is almost like 1 kilometer. It's very big building. In that building, in the area of robotics, we included the new technologies for the movement of both asset and people within the data center. But there's a difference between 1784 and 20C project. In 1784, robots deliver just small items, while in 20C, they move very large and heavyweight assets. And users in 1784 have very short and infrequent interaction with robots, but in 20C, users are mostly dedicated data center workers and who interact with robots for more than an hour per day. And these kind of differences affected the physical design as well as robot identity embodiment and the way of the robot interact with people. These are all the robots in data center. The first one is called GaRo, is for asset transport, and the second one, SeRo, for asset management, and the last one called ART-B for long distance support. Today I will focus on GaRo and SeRo, and especially on GaRo, which has more human interaction. GaRo is in Korean, horizontal in Korean, because this robot moves the assets in horizontal way. GaRo is a self-driving robot that moves heavy servers quickly and efficiently in Gak Sejong data center. It works with another robot, SeRo, to automate and streamline warehouse operations. GaRo uses eye-like indicators like this. To show its direction and status and adjust speed for safety around people. And workers can also manually control GaRo if they need it, but with built-in safety lights. And overall, GaRo reduces human workload and improves efficiency by collaborating with both people and other robots. And SeRo, vertical in Korean, it moves the servers in vertical way. That's why it's called SeRo. It's the robot that designed to safely and efficiently manage servers and assets, which are crucial in data center. It can load servers on its own and keep track of the asset history automatically. The robot, as I mentioned, also works smoothly with GaRo, another robot, and with needing any human help. For tasks that should involve the people, there is a robot station. It's kind of interface making collaboration safe and flexible between SeRo and the worker. It runs 24/7 and continuously managing assets to keep everything efficient.
What does a data center with robots look like? Let's explore an example of the asset transfer process from the warehouse to the server room. First, a data center worker assigns tasks to the robot using ARMS, or the AI Robot Management System. They simply select the asset information and send it to the robot system, needing only to add the task start time and location. Once a task is registered, the robot system assigns it to an available robot. SeRo, an asset management robot waiting at the charger, departs to retrieve the asset. SeRo moves to the rack with the registered server, uses OCR to verify the asset number, and retrieves the server. After a successful retrieval, the robot system updates the asset records automatically. SeRo loads the retrieved servers onto GaRo, the transport robot, following the order registered in the asset information to keep track of where each item is loaded. Once all servers are loaded, the robot system commands GaRo to move to the server room. GaRo autonomously drives to the destination inside the server room. At intersections, GaRo uses its display and LED to indicate its direction, preventing collisions with people. GaRo avoids sudden evasive movements to protect the asset and people. When it encounters an obstacle, it slows down, stops, and requests assistance to remove it. With help from ARC, the AI robot cloud, GaRo can use the building facilities. The ARC manipulates automated doors as well as freight elevators upon a request from the robot. It also allows GaRo to pass security gates and enter the server room. Upon arrival inside the server room, GaRo switches to authentication mode to prevent unauthorized control. The authorized worker scans their ID card to proceed with the task. Inside the server room, power assist mode is used instead of autonomous driving, allowing workers to manually move up to 400 kilograms of assets with minimal effort. In power assist mode, LED projects a safety zone onto the floor to prevent collisions, warning if objects enter the zone. When encountering obstacles ahead, it issues warnings. The warning level adjusts based on distance to avoid collisions, even with blind spots. Workers check the rack and hole positions displayed on the screen. It shows which server should be installed where and any additional steps needed. The worker checks if all servers are installed correctly, completing the task. Since autonomous driving is unsafe in cold zones, the worker moves the robot to the central aisle. After checking for any issues or incomplete tasks, the robot returns to the storage area. Upon worker confirmation, it autonomously drives back to the warehouse. At the warehouse, GaRo returns the cart, and then waits at the charger for the next task.
Now let's look at how the robot's interaction and functions in the video were derived and the design principles underneath of the functions. First, the robot size had a big impact on its navigational behavior. Its large size and weight make it feel more like a vehicle rather than the robot. And it can be intimidating and sudden evasion like those of small service robots. It could be dangerous for this robot. So instead of actively avoiding obstacles nearby, we decided to make the robot stop in front of the obstacles and give clear signals about its movement and keep a safe distance from people. And expectation for interactivity also influenced the robot's behavior and design. Since it mainly helps with physical tasks, it doesn't need a very close, like human-like interaction that the household robots have. However, users expect more than just a dumb machine that moves heavy items. They want a robot that can keep the data center data accurate and understand a task on its own and notify them about the important details. Even though it doesn't need to feel like human-like, it should still feel like a helpful partner, not just a simple machine. In addition to the robot's basic role, we wanted to define some clear design goals. To do this, we observed and interviewed data center workers about their routines. And this helped us understand their expectation and the stereotype of the future data center robots they have and the key requirements for successful operation of robotics system. We then defined 3 core values and set design principles to meet these values. The first one is that improving perceived safety. Protecting both assets and the workers is the top priority in data center. Technically, technology-wisely, the robot must ensure physical safety, and from interaction design view, workers should feel safe and secure when using it. And second value is work efficiency. The robot system should make existing tasks more efficient. Its purpose is to significantly reduce task loss, especially the physical demand on workers. The third value is acceptability. Since the robot will be used in practical, everyday tasks, it must be easy and comfortable to use frequently. And it should also be simple for workers to adapt the new system without much effort. With the design principles I mentioned, we identified several design features to achieve our core values. Today I would like to briefly share how these 3 features, including navigational, interaction, and collision warning, and information design for UI, were developed, and some design techniques and trials were used in the design process. About the navigational interaction, at the early stage of product design, we wanted to define global navigation behavior and compare different local navigation interaction expressions. But we faced limitation and challenges because the space was not ready because it was under construction. The actual data center was under construction, and the robot is not prepared because it's the hardware is under development and the software like navigating the robot is not yet fully developed. So with this feasibility, limited feasibility, we rather create interaction prototypes in VR and to test. For the space readiness, we use the conference room in our office as a substitute for the real environment. And for robot readiness, we developed a VR simulator with the MetaQuest and Unity, and which allowed us to design and test interactions without needing any hardware or robot software. And this is a short video on comparing interaction expression, feedback, design in local navigation. Is the real implementation on robot. You can see that on left side, there's nothing special interaction behavior, but on the right side, it blinks the LED and shows the direction on screen, and you can see the workers' behaviors were changed because of the interaction. We found VR simulation for designing robots' navigation interaction were highly effective. The overall results from VR experiments were generally consistent with those from physical experiments, and interactions that are difficult to implement with a robot can be maybe the sound is coming from video, I guess. Yeah, I can continue. And with the real robot, we don't have much resource and to make a test, make a prototype for the test on my own, on our own. But with the VR simulator, we can easily develop and test the behaviors and interaction expression. And it was also convenient for logging and analyzing movement location data. But VR simulator also has a fallacy. Since the sense of weight isn't felt in VR environment, people act more boldly, and in VR environment, they were not afraid if the robot they and the robot collides, but in reality, they sometimes be nervous for the collision. I wonder if the lack of visible body parts of the participant, it made less cautious about the collision in VR, and we thought from our experience, we thought that VR is where using VR is better for testing the smaller robots, comparing relatively smaller robots than GaRo. And if the if using VR for the bigger robot, maybe careful adjustment to sound and ambient lighting in VR are necessary. And we saw that the impact of LED expression is greater than real environment because of maybe the resolution of the VR device. And the visibility of LED lights in VR was significantly lower than the real environment. So for the interaction expressions like using light, it could be not a good option to use VR. And the second feature, for the collision warning, we wanted to validate the effectiveness of collision warning interaction and determine the best technical specification. But we faced several challenges. We had a kind of lack of shared understanding among team members, like including a project manager and the engineers and designer on this function, and we had the uncertainty around the validity of our approach, especially concerning sensing ability and internal software communication latency. To cope with these challenges, we developed a virtual simulator again, and this allowed us to test the effect of features that hadn't been implemented yet. And we created a Unity simulator that allows adjustment to input settings such as sensing area and distance, and change to the feedback, like including LED and sound. And we then had potential users and engineers who implement this function, let them experience this simulator and have a kind of a deep understanding of this function. And yeah. Yeah. And this is how the collision warning interaction looks like in your use case. This trial brought several benefits by transforming vague specification into concrete requirements, but there were still unsolved issues. From a project management standpoint, power sys mode received a lower priority, and the collision prevention as well. So yeah, and another challenge was gaining consensus on the importance and value of our work. We only presented simulation results to project manager, so maybe the manager fully emphasized on the impact of this interaction. Reflecting on this, we thought that we should involve project managers and project owners from the beginning of the simulation, might have fostered more alignment. And the last one, I don't have much time, about the testing the usability of the GUI of the robot. At the early stage in design, we aim to test the draft version of the information architecture, but we had COVID, so we cannot directly meet the real user in real context and with real device. So We tried to test it remotely using Zoom and the prototype, the interactive prototype. And to maximize the immersion during testing, we provided instructions and information based on real task data and the context. Maybe I should move on. The results from remote usability testing using Zoom and prototype align with those from physical usability tests conducted in real data center environments. I will conclude the presentation with some overall takeaways for data center robots. Safety and work efficiency and adaptability are the most important thing, and more important in the case of the service robot. And every design feature must be created to uphold these values. And developing robots take a long time. We almost spent 4 years, including the construction of the data center and building the robot. And involves many steps. So during the design process, there are often situations where the robot's hardware or software or even the physical spaces are not ready yet. So in these cases, simulations are always necessary and effective. Using VR to simulate interaction has proven especially helpful, as it can closely replicate the real physical environment and save a lot of time and effort in the design process. And it's also crucial to let both users and the important stakeholders experience the simulations. In production, setting priorities and building agreement is very important. By involving users and stakeholders as often as possible during simulation, and by choosing the right tools for this, we can ensure everyone is on the same page and make the possibility of implementing design features in reality higher. Yeah. Thank you for the listening.